इंटरनेट से कनेक्ट हुआ हूं मैं।
ओके सर।
मेरा स्क्रीन दिख रहा है आपको?
यस सर, स्क्रीन इज विजिबल।
Okay, then I can start.
Yes sir. Swati?
You can introduce if you want to give any introduction.
Yes sir, we are giving.
Yes, sir. Yes.
Vikram, kindly introduce the expert. Okay. And
Okay, sir. Okay, sir.
Okay.
Good morning, sir. Good morning to
good
all
morning.
participants, speakers, and faculties. We are honored to have Professor Rajveer Singh Yadwansi, sir, from NSUT Delhi for this session. First, let me introduce to Professor Rajveer Singh Yadwansi, sir. Professor Rajveer Singh Yadwansi is a professor at the Netaji Subhas University of Technology, Department of Electronics and Communication Engineering. He has obtained a Master of Engineering in ECE from MNNIT Allahabad and PhD from Delhi University. He has more than 35 years of experience in the fields of RF and microwave engineering. He has published 3 books on antennas, 1 rectangular DRA theory and design in Springer, 2nd nano DRA for 5G applications in CRC press, and 3rd terahertz dielectric resonator antenna for high speed communication and sensor in IET. He has published 1 patent and more than 116 research papers. He has organized the international conference ICPR 2017 in Delhi as General Chair. He has worked as Dean R&D at East Campus and Senior Scientific Officer in Defense Ministry and Chairman Selection Committee and Ministry of IT, Government of India. He is selected in EQDC Gujarat as director in 2016. He has visited to France as team leader in radar modernization program at Defense Ministry. He is a reviewer of IEEE transactions, antenna and propagation, IEEE letters, WPC and AEUE journals. He is awarded excellence in academic and management. His research area includes RF and microwave, sensors, MIMO dielectric resonator antenna, absorber, IoT, and filter design and implementation. Thank you, sir.
Thank you. Thank
Over
you
to
very
you.
much. Can I start now?
Yes, sir.
Okay, I'm very much thankful to the organizing team and in specific to Dr. Singhal for giving me the invitation to talk about terahertz designs. Now we are already familiar with the word terahertz. Can I know the audience are from which background? Vikram, can you specify the audience are from which background?
Sir, most
Sir, all the audience are, all the participants are either PhD students or they are faculty members from different institutes.
These are all from
From the-
electronics or from others also?
All electronics,
Okay.
electronics and physics.
Okay, thank you. So, terahertz, because this conference deals with terahertz, and we are switching. India is very much familiar with the word 6G, and lot of research is going on for developing devices for 6G communication. And the terahertz will play a crucial role in to develop the devices. IIT Chennai, IIT Madras is doing wonderful task on 6G communication system, and they are devising a lot of devices, especially Bharat Alliance has been given task to develop the devices on 6G communications. So we are also taking lead to devise these terahertz devices. Today I'll talk about terahertz sensor, and in specific terahertz absorber we will take help to devise these sensors. and we are focusing to develop non-invasive blood glucose sensors. We will be making use of terahertz absorber to proceed further to have design of non-invasive blood glucose sensors. Before I go in detail, I'll give you brief introduction and status of this particular area. I have done a lot of survey and found that there is no sufficient research to develop non-invasive blood glucose sensor globally. I'm not talking about India, but globally. And there is no single device exists which can monitor your blood glucose level without giving a prick or without or having non-invasive techniques. I again repeat, the FDA approved device is not available, though the market is flooded with saying that our device is able to monitor non-invasively, but FDA has not approved any single device, neither the watches available in the market. Apple also came into the existence long back, but they withdrawn. Then the Samsung also came into the market and they withdrawn. So people should work in this domain. And we also tried to develop a sensor which will be based on terahertz absorber. So when I say absorber and when I say antenna, the philosophy or the mechanism of working terahertz antenna and terahertz absorber is entirely different. Though in last week we made a wonderful research by applying both the technique to devise a compact antenna, and we will be using this compact antenna not at terahertz for very low frequency. So it was a wonderful breakthrough, though the patent we are about to file on this. There we have applied both approach. We designed an antenna, but applied absorber techniques into it. By this technique, we are able to minimize the size of the antenna. Otherwise, the size at GPS frequency will be very large. But because of applying the absorber technique, we are able to get the dimensions of GPS antenna in millimeters. So that I'll talk in separate lecture. But today I'll focus on the concept of designing sensor using terahertz absorber. Now, if you see the first slide, we have given you the diagrams terahertz absorber. If you see here, in this, the first figure is ultra wideband absorber. The second figure, narrow band absorber, and in third figure, you will see the pole model is being used to develop the sensor. That is terahertz sensor, where you will find nail, bone, blood, fat, skin. And in third diagram, you will find that a finger housing has been developed for developing non-invasive blood glucose sensor. Coming to the design of absorber, here you will find we have to start from the scratch, and you will find that there is a flinked port, and this flinked port is the basic element to design the terahertz absorber. Now here you will find flinked port 1, flinked port 2, and the periodic boundary conditions. So similar to antenna, what we design, we have a box, radiation box. Here we need to define the periodic boundary condition, flinked port 1, flinked port 2. Now the design of absorber is basically based on constructive. There is a term known as constructive interference, where we use to get high directivity in antenna, but here it is reverse. When we design absorber, it is based on destructive interference theory. So constructive interference theory we use for gain enhancement or getting high directivity, and destructive interference theory we apply to have high absorption. So here these are the well-known techniques, the constructive interference theory and destructive interference theory. So the antenna is The high gain antennas even at terahertz frequency are based on constructive interference theory, but the absorbers are based on destructive interference theory. And the details we'll see later on is given in this diagram. If you'll see here, there are various reasons. And here in designing absorber, we generally use FSS, and we also use IRS. We'll come back what is this IRS and what is FSS. But here you'll find basically these are the elements, and then based on the ground plane, then the absorption of the material will depend on the substrate too. So we'll see that how the absorbers are designed at terahertz frequency using destructive interference. Now, when we say flinked port, the flinked port can be combined with perfect electrical boundaries and perfect magnetic boundary conditions. The structure of absorber is based on lambda by 4 principle. We invoke flinked port using boundary conditions either T or Tm or combination of T and Tm. We select number of modes started from 2 as per desired applications, and then we run simulations. These are the basic elements we cater for designing the absorbers. Here are few, we'll discuss more, but here are few basic mathematical theory. We generally observe DNG, that is double negative material, or SNG, single negative material. And then we carry out the material, and we will use the not natural materials but artificially developed material. Those are known as metamaterial. And then based on the theory of destructive interference, we carry out and control the incident angle, we control absorption, we control polarization. That we'll see in the later part. So these are the mathematical theory which are based on destructive interference. Now, this is very important slide here. Metamaterial characteristics. As I already told you, that here the Snell's law will not be followed, but we alter that Snell's law. And that we can do only by developing a artificial materials, not the natural materials available. And these artificially developed materials are known as metamaterial. How we alter characteristics of material? Here, this slide will be able to give you a focal point. The main parameters of absorbers, we keep the impedance, input impedance, 377 ohm, which is free space impedance. The negative refractive index is being obtained. We'll see how we will be able to get this negative refractive index material. TE, TM polarizations, both we can play with. Here in absorber, the loop current is being intently formed. When loop current is formed, the magnetic field generation will take place. At the moment magnetic field generation takes place, the absorption happens. And if we are able to create this absorption, we will say at particle frequency and particle wave bandwidth, then we'll say we are able to successfully design a absorber, in particular terahertz absorber. Sometime we will require polarization insensitivity, or sometimes we require polarization sensitive TE or TM mode. So both features can be obtained. We'll see while we design that we are successfully able to obtain the polarization sensitivity or polarization insensitivity. Especially in RF energy harvesting, we require that from any angle we are able to receive. And even in stealth, when we go for stealth, we want that the incident signals received from any angle should be absorbed. So both are required parameters. We need to control incidence angle. The wider is the incidence angle, better will be the absorber. And now, if we see the diagram here depicted, It is in all four quadrants. So one indicates double positive materials, that is being represented by DPS, mu greater than 0, epsilon greater than 0. Both these type of materials are generally found in nature, and we use them for devising antennas. Now, second quadrant, here you see that mu is greater than 0, epsilon is lesser than 0. We call them a negative material. Then third quadrant, we have DNG, mu lesser than 0, epsilon lesser than 0. And these both DNG materials, double negative, because mu is also negative and epsilon is also negative. So we call them the double negative materials. Then the fourth quadrant, mu. So for absorber, generally we stick to this particular diagram, which is able to provide us mu negative and epsilon also negative. Then the last quadrant, fourth quadrant, mu is lesser than 0, epsilon is also lesser than 0. So these are mu negative materials. So for designing high performance absorber, we stick to metamaterial, and these are double negative material where mu is also lesser than 0 and epsilon is also lesser than 0. Now, this slide is very important. We have created a slide which has absorber features and antenna features. For antenna, generally, we take lambda by 2 design, but for absorber, the size of absorber is lambda by 4. For antenna, the impedance is generally 50 ohm, but here the impedance is 377 ohm. In absorber, the material characterization, as I already specified, we generally go for DNG, which is double negative, and for antenna, we go for positive characteristics, that's DPS. For these are the material which are being used as DNG for absorber. These are artificially designed material, and for antenna, these are generally found in nature. So negative reflectance is being obtained using those material in case of the absorber, and there we use positive reflector index material. Now, flinked port is used as feed here. There microstrip line, nano waveguide, and these other feed types are available in designing antenna. In antenna, we feel that dipole formations are taking place, mode generation is taking place, resonant circuit is being developed. Here also, out of these, the resonant circuit is available, mode generation is available, but there is no dipole formation as far as absorber is concerned. Then in antenna, we go for power gain, summation of dipole moment, or combination of wavefront. Here, the power absorption is because of we have the FSS, and based on FSS, the resonance will be there, and from resonance, the current formation will be there. From loop current formation, magnetic field will be there. From magnetic field, then absorption will take place, because the heat it is converted into heat, and then it works. The absorber works in receive mode, whereas antenna works in both receive as well as trans mode. Size of linked port is generally taken more than lambda by 4. Here we have seen size of radiation box is generally taken more than lambda by 4. There is a pattern, specific pattern in case of antenna, but there is no absorption pattern. Operates based on interference theory as far as absorber is concerned. The operates on constructor interference theory. These are the main points which either to design of antenna or to design absorbers. Now, working mechanism of absorber. As you see here, incident wave received by resonant circuit built by frequency selective surface, and it is designed based on RLC circuit. The RLC equivalent circuit will specify the to creation of resonant, and it will be for particular frequency. Now, electric field component of incident wave excites free electrons in case of absorber. So these free electrons constitute surface current, and the surface current will cater to loop current, and the loop current will cater to magnetic field generation, and magnetic field generation will carry out to the losses, and these losses will be corresponding to the absorption. Now surface current enter into substrate only if it is a DNG material. So phase change takes place here. The phase change take place, and these phase change will be lesser than 90 degree. Now the absorption phenomena will be depending on the incident frequency, and due to ground plane, the absorber will have ground plane, and due to this ground plane, based on interference theory, the multiple reflections take place, and based on multiple reflections, we get high absorbance. So multiple reflections takes place into the substrate because of ground plane, and these are due to change in refractive index, as we already iterated that DNG formation is there. Anti-parallel currents get constituted in the ground plane with respect to surface. Thus, we have already told you this. Due to this loop current formation of magnet, and because of this magnetic absorption, the exhaust power in absorber is dissipated at heat based on law of conservation, because energy can neither be created nor be destroyed. Now, based on this working mechanism of the absorber, we have certain parameters which we need to look upon. The first parameter is S11, that is reflection coefficient. Second parameter is absorption. Third parameter is incidence angle. Fourth parameter is polarization angle. Next parameter is impedance, generally equal to free space. The absorber will have certain amount of bandwidth. Absorber will have multiple resonant modes, and basic this is what we need to look upon, how to create these resonant modes. Total theory of absorber is based on creation of resonant modes and manipulation of these resonant modes. Of course, in antenna theory also, when we talk about dielectric resonator antennas, we create the resonant modes, we play with these resonant modes. Either we merge these resonant modes, either we displace these resonant modes. So in antenna theory, we create resonant modes, fundamental modes, higher order modes, and play with these higher order modes to manipulate bandwidth, to manipulate gain, to manipulate resonant frequency, to manipulate the polarization, RSCP, LSCP, to manipulate whether it is multiple bands, whether it is narrow band, whether it is wide band, whether it is circular polarized, whether it is highly directive. So these all features we can control with the resonant modes. And in absorber also, similar theory will play. So we can develop the developing or generation of resonant modes is in the designer hands. And if designer is able to generate these resonant modes, he can tune, he can play with these resonant modes, and based on the design and control on resonant modes, the designer can develop any sorts of antenna and any sorts of absorber, whether it is wideband, whether it is narrowband, whether it is polarization sensitive, whether it is polarization insensitive, whether it is high gain, whether it is a high absorption. These all things can be controlled with this one feature, that is resonant modes, and we have done this. even in antennas as well as in absorbers. And not only absorber and antennas, even utilizing both at one go. We'll see that. Equivalent RLC circuit realization, surface current, E field and H field. Now, these generation of E field and H field will let us know the situation of resonant modes. How these resonant modes are being used to create the specific E field and specific H field patterns. So both things are in designer hands. We'll see them. This is simple structure I picked up for illustration that how a absorber is designed. So this is EMR or FSS. The incidental signal of specific frequency hits this EMR or FSS. Now, if it is DNG, the phase change takes place, alters Snell's law, enter into the substrate. Here, substrate is SiO2, reaches to ground plane. Ground plane is generally PEC, hits to ground plane and come back. Now, restrictive interference theory will take place. Multiple reflections will occur. These multiple reflections based on phase control will take place, and the summation of all these, as was depicted in the equation, will result into the absorption and other absorber parameter such as polarization, incidence angle, and absorption. These are the major parameters into absorber. So this is basic design we are able to depict as far as absorber is concerned. If you see here another diagram, this particular diagram is at different frequency. We'll see that. Now, if you see here, now this is terahertz absorber design, and this is terahertz antenna design. We can differentiate the design here. Here, FSS is there, but this FSS is not having that characteristics which a DNG was. It is of DPS. Now, there is a different feed techniques as far as absorber is concerned. Here it is silver nano waveguide with Gaussian beam. Input excitation is taken, and then the reception and transmission, both the fields are being controlled by similar technique which were incorporated in absorber design. So this particular diagram has depicted as terahertz antenna, and this particular diagram has depicted structure of terahertz absorber. You yourself can visualize the difference between this and difference between this structure. Now I come back to absorber. So theory of design of absorber, if you see here, of course, okay, let us see this first. Now this is incidence terahertz signal. If it is natural material, it is supposed to travel as being depicted with the red signal. Here also you will see in the diagram general behavior of signal in material. I'll not use here metamaterial term, but I'll use material only. And these are positive material mu as well as epsilon. This follows Snell's law. If you see here, there is the dotted line. So now the blue line depicts that it has certain amount of deviation from the general behavior of the signal, and it is being manipulated by the designer by choosing a particular value of reflective or index or mu or epsilon. And by using that DNG property, we are able to manipulate the signal when it's entered into the substrate, and the signal has turned into the blue. This is known as negative reflection, and it is this property is also termed as metamaterial property. It means while we design an observer, we create these material in such a way that we are able to alter mu and epsilon, or mu r or epsilon r. Now come back to the theory. Now here you will see there is a FSS written in this particular diagram. There is a epsilon r, epsilon dash r minus j epsilon double dash r, and on the bottom you will find that there is a ground plane. Now the FSS is frequency selective surface. Now because of this particular surface, it has altered the received incident signals, and it enters into substrate by manipulated angle or disobeying the Snell's law with this equation known as epsilon r is equal to this. So a complex permittivity will play into role, and because of this you will get the incident signal to reach to the ground plane, and because of the electric conducting wall, it is a electrically conducting surface, the signal is reflected back, hits to FSS, comes back, hits to ground, comes back, and because of these destructive interference, theory is well known, already developed, we are able to create absorption into the substrate, and this absorption will be controlled by destructive interference theory. The D will regulate. Now, how it will regulate? Here you will see the mathematical formulations. Equivalent circuit diagram of absorber is being depicted here. If you see here, there is a this D substrate. Here Z is the frequency selective surface. This is metal G, Z, G and D, and you will find these equations being realized based on the equivalent RLC circuit. Z I is equal to ZG plus ZS. So from this, we need to see that 377 ohm is equal to Z total, which is nothing but from this circuit we see ZFS parallel to ZI, and from this we can get this particular ZI equation which is depicted here. Similar to now here we get ZI. Similar thing we have already seen while designing terrace antenna. The surface will be a deciding factor, and the transcendental equation will regulate that as far as antenna theory is concerned. Now this is being depicted. Now if you see, based on this particular equivalent circuit, we are able to create different structures. This is one. If we create structure like this, we are able to get ultra wideband response. If we create similar structure like this, we are able to create narrow band. So for developing blood glucose sensors, we have used narrow band configuration, and excellent response we are able to achieve with this particular structure. So these, depending on the FSS structure, we are able to realize the wideband characteristics as well as narrowband characteristics. Now, in designing blood glucose sensors, we have taken help of the Cole model as being depicted here. We have also taken Davy model, and we have differentiated Cole and Davy model, and we could reach to a conclusion that Cole model is advanced as far as Davy model is concerned. So we have used this Cole model to design our non-invasive blood glucose sensor. Now, if you see here, what is Cole model? The human phantom is being depicted by using the materials artificially being developed. The nail is represented with some permeability, the bone is represented with some permeability, the blood is represented by some permeability, fat is represented by different characteristics, skin is represented by different characteristics. So these the Cole models are theoretical models, well developed by chemistry and physics people. We have utilized only that particular, we have not developed Cole model, we have utilized those features and invoked into our design so that we can mimic the skin and the finger, bone, etc. characteristics to get our simulated result, so that we can have the total quantity of the blood glucose molecules and see how much these molecules are available in particular volume, and then based on calibration we could identify that how much molecules are there, how much the based on the resonance or resonant characteristics we are able to define how much is the heat, or before that how much is the absorption, and then the calibrated response is being depicted to get you into the corresponding voltage, and these corresponding voltages which are very small in amount is being amplified, and these amplified voltage is being calibrated to represent how much absorption or blood glucose absorption takes place in MGTL. That is what we created. Now, the showing you this particular diagram only depicts that the FSS characteristics are being invoked for carrying out the absorption at terahertz frequency. As far as specific frequency is concerned, we have used 176 for our simulations. Why we have used 176 terahertz? There is a theory behind that. We'll come back. So, if you see this particular figure, we are able to create narrow band characteristics and multiple bands also. Now, if you see this particular, we have created a cavity for placing our finger based on Cole model, and then draw the inference that how much is the absorption response, so that we can calibrate into the blood glucose levels. So here, air cavity, if you see, there is a finger chamber. Finger chamber is being depicted with the finger as fat, bone, etc., etc. What are the finger characteristics are there? Now, mechanism, how we develop that particular sensor is being depicted. So if you see here, A, step A involved, this particular shape, and I'll be able to show you the response also. So terahertz response I'll be showing in the next slide, but the figure, the steps we were involved like this. First, we developed this particular a circular or cylindrical nature of FSS, and then we created in step 2, we cut this particular material, and in step 3 we created this particular shape. In step 4 we created this particular, if you see here, this shape, and consequently we created this particular shape as being depicted in figure 4 and figure 5. In figure F, you see that FSS is being represented by T1, and the substrate is represented by T2, and ground plane is represented by TS. Now, after we successfully designed the structure, we carried out some sorts of parameter simulations. In parameter simulations, we obtained, see figure A, we computed polarization angle. In figure B, we computed incidence angle. In figure C, again, can anyone differentiate between figure C and figure A? You will find that there is a difference. We'll come back. Similarly, incidence angle in figure B and figure D, there is some difference, though frequency same. We'll come back. So here you see this is being simulated in T mode. Here it is simulated in TM mode. Similarly, here we have simulated T mode. Here we have simulated TM mode. So both response we have carried out during simulations. The frequency obtained 2.5 terahertz to 9.5 terahertz. Now, if you see these plots, we have obtained S11 in dB frequency 0 to 10 terahertz. So different characteristics are available. For one, if you see 2 into 10 to the power 5 Siemens per meter, 1 into 10 to the power 5, and 3 into 10 to the power 5 Siemens meters. So here you find that there is a different S11 being obtained. These characteristics we have utilized for developing the sensing or sensor parameters. Now, if this was about reflection coefficient. Now, absorption, you will feel that the absorption also will depend on different the characteristics of this. You will find that there is a variation in absorption also, and we have carried out 4 to 8 teras. We could obtain more than 90% of the absorption. If you see here band, more than 90 from here to here, you are able to get more than 90% absorption. So these are generally being features chosen that if your absorption is more than 90%, it means you are able to successfully design a good absorber with a high efficiency as far as absorption. Now you see this particular slide. These are the being fields plotted. There are absorber. These resonant modes are being well visible here. E and H fields. Figure A, you will see that this is like the resonant modes are being depicted with these arrows in circle form. And here you will feel that you can depict these fields in XY, in XZ, and even in YZ. So there is already a well-known mode theory. Even if we employ dielectric resonator antennas, we are able to create XY, XZ, and YZ. And then we can differentiate what type of mode is excited, and based on that the complete theory of resonance is being defined, and we are using those mode theory either for mode merging. By mode merging we are able to get wide band applications antennas as far as terahertz frequency is concerned. Then we can split these modes, and by splitting those resonant modes in terahertz antenna, we are able to get multiple bands. So the mode theory is well established. By simply controlling these modes, the all antenna parameters can be controlled. And in similar scenario, we will see here in terahertz absorber also, we are able to control the absorber parameters by simply controlling the excited resonance modes. Here, there are few more parameters. You will see that I have shown you the design process of step 1, step 2, step 3, step 4, step 5, and based on those simulations obtained, we are able to get absorption response. Here, the absorption response has been plotted from 0 to 10 terahertz, and step 1, you will see here, this graph represents step 1 absorption. Here, step 2 response, step 3 response, and here step 4 response, here step 5 response. So these all the design steps has been depicted in the response as far as absorber is concerned. So now similar steps has been incorporated and being depicted here in these diagrams. So for you can see the S11 at dotted S1 and green S1N and these pink color dotted has different permittive materials, and then we are able to define the resonance which we can make use of. So structure and depending on the materials, both we are able to depict the response. Now, as I already said, that we have used coal model and Devi model. So in coal model, if you see here closely, if you see here this particular table, we are able to represent our skin with the 60 value, blood, bone, nail, and fat with 5, 40, and 20 value. Now, these are the different values of alpha, omega c, and epsilon infinity. Now, if you see here our design, we have taken our dimensions as T1, T2, Ts already depicted in earlier diagram, R1 as these values in micrometer, and these values in all dimensions are taken in micrometer. So these are the design dimensions we have utilized to develop our RF or terahertz absorber. We have compared the results also. If you see here, there are various literature available in terahertz absorber. For literature which we have taken reference of, few authors have used VO2 as substrate, metal and graphene being used to design absorber, patch and graphene, 3 to 2 to 7, I think terahertz, dielectric, graphite and dielectric, metal and graphene. It means graphene is also being used to develop terahertz absorber. Again, in this particular reference, VO2 has been taken as substrate, graphite dielectric, VO2 is taken, metal dielectric, VO2 graphene and metal. Okay, and if you see 2023, there is a reference which is used at 0.94 to 4.35 terahertz. So that author has used VO2 as substrate, graphene as FSS, and metal as ground plane. Again, VO2, SiO2, polysilicon, these are the material being used to design 5.84 to 12.1. Then graphene, metal, AU. If you see 2024, AU, SiO2, these two different materials have been used to devise absorber, and it spans to 2.42 to 6.11 terahertz. We have used metal dielectric metal, and our frequency was 2.5 to 9 terahertz. So here, if you see comparatively, we are able to get the higher bandwidth of our absorber. Now let us see the fields. Now here we have plotted our H fields in the absorber, and these are the fields we are able to depict. This is H field A oblique M, and here in this structure we have used 2 into 2 array. Now by using this array, we are able to get, you see this particular diagram where the absorption is plotted and the S11 is being plotted at same axis. You will find that the absorption is 100%. So excellent design of absorber, and the below diagram shows the frequency at terahertz. The y-axis shows the magnitude. So S11 as well as absorption both are being plotted on the same diagram. This is the structure of absorber. So from this particular structure, we are able to illustrate that we can develop ultra wideband absorbers. At the same go, we can obtain very high absorption rate by constituting a array design of the absorber and using multiple rings as the FSS structure. This is the theory. I'll not read out this because already it has been. This absorber basically we are controlling N, and then based on N, we are able to develop a highly narrowband absorber, and these narrowband absorbers are being specific to a particular frequency. We can use to design the sensor because narrowband has good response as far as sensing is concerned. Generally, the sensor design uses shift in frequency, shift in magnitude, shift in phase, or any other characteristics, and those shifted characteristics are being calibrated to determine the blood glucose levels, and these are all being used to design a non-invasive blood glucose sensor. We have made use of these at 176 teras. Any questions?
Hello.
Any questions?
Yes, sir.
Yeah, please.
Sir, you told only a double negative material allowed EM waves to penetrate into substrate.
Hmm.
Can single negative materials
Yes,
doesn't allow?
yes. Single, double negative material is better, but we can use single negative material also.
Okay, sir. That means if any absorber is absorbing, that means it is having single negative or double negative.
Both we can play with.
Okay. And the second question is, sir, what is the difference between H field and surface current in CST? If you see the arrow by seeing this structure in arrow symbol or in a contour plot, then what is the difference between this H field and surface current?
Basically, what you are in CST, either you can take arrow will be there in all.
Yes, sir.
But the options are available, whether you want to have surface current, whether you want to have surface density, whether you want to have H field, whether you want to have E field. So that will make the difference which plot you are going to take.
Okay, suppose, sir, if I am taking the arrow plot in H field as well as in surface current, that means that both the images are similar, no?
No, but option is different. Whether you are taking E field in CST, that will let you know whether you are plotting E field or you are plotting surface current. Arrow will be there. Arrow will be there in both. Arrow will be there even in E field. Arrow will be there even in H field.
Yes.
Arrow will be there even in current density J.
No, sir, my question is, suppose I am taking E field.
No, but you will find the units also difference will be there, na?
Yeah.
A by M and V by M.
Yes.
Those units also will be different.
Yes, sir, yes. Units are
Mm.
sure. Yes.
I think there is no question, and then I can exit now. Okay, Vikram, thank you.
Sir,
Yeah.
sir, there is a query in the chat box. So participants are raising their query in the chat box.
Okay, please
The-
go ahead then.
Yeah, the first question is, if impedance are matched in absorber, then how it absorb EM wave?
Impedance is impedance is matched even in antenna as 50 ohm. Impedance is matched in absorber as 377 ohm. So it is to receive them and minimize losses, and then the phase change will take place. So impedance is required to be matched in both the cases.
Okay. Second question is, sir, what are the tools required to design terahertz absorber and antenna?
Only CST.
Okay.
CST is sufficient for both.
Yes. Okay, sir, you can continue. We will take the remaining queries later.
If any question is there, we can discuss.
One more question is there, sir. Can you explain surface current density plot in the slides in some detail and how it is useful on generating ECM offset?
I do not have any But we can definitely, using CST or HFSS, we can plot them. The option is available.
Sir, the question is how the surface current is important or useful on generating ECM of it.
How?
How surface current density is useful on generating ECM of any structure, any absorber structure.
See, basically, J, we can, in CST and in HFSS, the option is available to plot J, to plot E, to plot H, to to plot, these options are available. So this basically the mode configuration will not be known without of E plane, H plane and J. So the modes, basically these arrows which we represent with the resonant boards, modes are basically telling you the signature being generated in terms of surface current, and same will get reflected in terms of radiation pattern in case of antenna, and in case of polarization sensitivity in observer. So these plots are very important, because how the current takes shape into the substrate is well known before the outcome is available. So designer has the capability to know how my antenna or how my observer will behave in near field and far field.
Okay.
Any other question?
Okay.
Okay. Thank you.
Thank you, participant. This session concludes here. We will now take a lunch break and our next session will begin at 4 p.m.